The universe's first galaxies are not what they should be. Astronomers peering back in time are finding cosmic infants that act like fully grown adults, a discovery that shatters our core theories of cosmic evolution. By the end of this journey, you will understand how these anomalies are forcing a complete rewrite of the universe's origin story. We will investigate why some of the earliest galaxies appear impossibly mature, and what mysterious forces could be warping the fabric of space itself. How do you think our deepest cosmic truths will change next? That ancient light traveling across the cosmos is our only window into the universe's infancy. To catch this faint whisper from the edge of time, astronomers rely on incredible machines like the Hubble Space Telescope and its revolutionary successor, the James Webb Space Telescope. These observatories act as humanity's ultimate time machines. They do not look across mere space, but deep into the past. The light from the very first galaxies has been journeying for over 13 billion years to finally reach our instruments. During its immense voyage, the expanding universe itself has stretched this light, transforming it. What began as visible light has been pulled into the longer, invisible wavelengths of infrared. This stretching effect is what scientists call redshift. The more stretched the light, the farther the galaxy and the deeper back in time we are seeing. By carefully analyzing this faint, redshifted glow, researchers can decode the galaxy's secrets. They can determine what elements it contains, estimate its total mass, and even discern its shape. This entire process is a staggering feat of human curiosity and engineering. It is how we are discovering that the early universe was not a simple, primitive place, but a realm of profound and puzzling complexity. With this cosmic time machine now understood, the real shock emerges when we look at the pictures it is sending back to us. The first shocking images from the cosmic frontier revealed a nursery that defied all expectation. Instead of finding simple, infant galaxies, astronomers saw what looked like fully grown adults. Theoretical models had long predicted that the universe's first star systems would be small, chaotic, and messy, struggling to form their first few stars. The reality is a cosmic paradox. We are observing galaxies that are not only massive but also surprisingly well-ordered, with immense disks and spiral arms. Even more telling, their light carries the chemical signature of vast amounts of cosmic dust and heavy elements. Think of it as walking into a nursery and finding, among the newborns, a teenager who has already lived a full and complex life. The presence of elements like carbon, silicon, and oxygen is the crucial clue. These materials are not born with the universe. They are forged in the nuclear furnaces of stars and then scattered across space only when those stars die in violent supernova explosions. Finding them in such abundance so early means that entire generations of stars had to be born, live their lives, and explode, all within a breathtakingly short window of cosmic time. This is premature maturity on a galactic scale, and it presents a fundamental challenge to our story of how the universe grew up. It suggests that the early cosmos was a far more efficient and rapid star forge than we ever dreamed, operating under rules we are only beginning to glimpse. This star-making frenzy introduces the second great shock from the early cosmos. The rate of star birth is a galaxy's heartbeat, a direct measure of its cosmic vitality. We naturally assumed that in the universe's infancy, this pulse would be slow and unsteady, a gradual flickering to life. The reality is a roaring, unstoppable firestorm. We are finding starburst galaxies that form stars hundreds, even thousands of times faster than our own peaceful Milky Way. Imagine a single, quiet campfire. Now picture an entire forest ablaze, consuming fuel at an unimaginable rate. That is the scale of the difference. These cosmic infernos shine with a staggering brilliance, their light a testament to an almost violent fertility. Such prolific activity demands two things: vast reservoirs of cold gas to act as fuel, and a powerful, efficient trigger to ignite it all at once. So what could possibly kick-start these stellar nurseries on such a colossal scale so soon after the universe began? The answer seems to lie in extreme environmental conditions, far more intense than we ever modeled. Perhaps cataclysmic collisions between young galaxies were commonplace, violently compressing immense clouds of gas and sparking these epic bursts of creation. Or maybe the early universe itself was simply a denser, more turbulent place, where gravity worked with a speed and efficiency we are only now beginning to comprehend. This anomaly does not just hint at a faster timeline, it screams of a fundamental misunderstanding of the very forces that built the first structures in the cosmos. And if the birth of stars was this explosive, what about their deaths? These stellar infernos, however, cannot burn without an invisible framework to contain them. This brings us to the third and perhaps most profound puzzle: the bizarre behavior of dark matter in these ancient realms. We have long known that this mysterious, invisible substance forms the hidden skeleton of the cosmos, a gravitational glue holding galaxies together. In our modern, local universe, dark matter typically arranges itself in a vast, diffuse halo around a galaxy, its influence gently guiding the motions of stars. But when we look at the earliest galaxies, that familiar scaffolding seems to warp into strange new shapes. Instead of the predicted smooth distribution, the dark matter halos around these infant galaxies appear astonishingly dense and lumpy. Some show profiles that astronomers describe as chord, like an apple with its center scooped out, while others are overly cuspy, with gravity sharply concentrated at their heart. You can think of it like building a house. We have a blueprint that has worked perfectly for billions of years, showing us how to construct a stable, familiar foundation. But when we look at the universe's first structures, we find foundations that are built completely differently, with some corners too heavy and others strangely hollow. This architectural anomaly has real consequences. It changes how these primordial galaxies spin, and it warps the light from objects behind them in ways that defy our predictions. What could cause dark matter, the universe's most stable construction material, to behave so erratically in its youth? This discrepancy suggests that our very understanding of dark matter's fundamental nature may be flawed. Perhaps it interacted with normal matter in the early universe in ways we have not yet imagined, through forces now dormant. Or maybe dark matter itself is more complex than a single, simple particle. Solving this mystery is not just about fixing a detail in our models. It is about questioning the invisible framework of reality itself, a framework that may be governed by physics we have yet to discover. But the true shock comes not just from what these galaxies contain, but from the breathtaking forms they take. The shapes of galaxies are their autobiography, a permanent record of the forces that shape them across cosmic time. We were certain the universe's first galaxies would be simple, chaotic blobs, the basic building blocks that would only later merge into the majestic spirals and smooth ellipticals we see today. This fundamental prediction has been completely overturned. The James Webb Space Telescope is sending back portraits of galaxies from an era when the universe was a mere infant, and they are anything but simple. We are seeing well-defined disks, elegant spiral arms, and even barred structures, a familiar galactic shape where a central bar of stars cuts across the core. It is like finding perfectly formed, intricate snowflakes in a cloud of water vapor, long before the physics of their formation should have been possible. The emergence of such sophisticated architecture so quickly is a profound puzzle. It tells us that the physical processes which create disk stability and carve out spiral arms were not slow, gradual events. They were operating with a breathtaking, almost pre-programmed efficiency from the very beginning. This discovery strikes at the heart of the hierarchical model of galaxy formation. the long-held idea that small pieces slowly assembled into larger, more complex structures over billions of years. The early universe was not a calm, primitive soup. It was a dynamic and intensely structured workshop, building intricate cosmic engines on a timescale we are struggling to comprehend. These immense glowing clouds are the fifth great mystery from the edge of time. While we study the galaxies themselves, our telescopes have revealed something even more vast and enigmatic surrounding them. In the profound darkness of the cosmic dawn, the first light to break free was a specific type of emission from hydrogen atoms, known as Lyman alpha light. Today, we see this ancient glow not just from galaxies, but from colossal, ghostly clouds that dwarf them. These are the Lyman alpha blobs, immense structures that can stretch for hundreds of thousands of light years, making their central galaxies look like tiny, bright seeds at the heart of a cosmic fog. Their sheer scale is difficult to grasp. If you placed one of these blobs where our Milky Way sits, it would engulf our entire galactic neighborhood and far beyond, a faint, glowing ocean of primordial matter. The origin of their brilliant glow is a heated debate. One possibility is that they are illuminated from within by the ferocious energy of billions of newborn stars, their collective light causing the surrounding hydrogen gas to fluoresce, like a cosmic street lamp illuminating a vast fog. Another theory points to the incredible power of active galactic nuclei, where supermassive black holes devour matter and blast out enough radiation to light up the entire surrounding gas cloud. Or perhaps these halos are fueled by something more fundamental, colossal rivers of cold gas streaming onto the galaxy from the cosmic web, glowing with the heat of their own dramatic descent. Their existence tells us that a galaxy is not an island. It is the visible core of a much larger, dynamic, and energetic system. These blobs are likely the primary feeding mechanism for the frantic star formation we see, representing vast reservoirs of raw material being drawn into the galactic core. To witness this process is to see the universe in its most vital and active state, a continuous cycle of cosmic construction on a scale we are only just beginning to comprehend. The brilliance of these early galaxies is rivaled only by the most extreme objects in the cosmos, the quasars. These are not galaxies themselves, but the furious hearts of galaxies, where a supermassive black hole feasts on surrounding matter. As this material spirals inward, it compresses and heats to millions of degrees, unleashing a torrent of light so intense it can outshine every star in its host galaxy combined. For decades, our models insisted that building such a cosmic monster was a slow, gradual process, requiring billions of years of steady growth. The universe, it seems, did not get the memo. We are now observing fully formed quasars blazing in an era when the universe was less than 1 billion years old. To put that in perspective, it is like discovering a towering, ancient redwood tree sprouting from the soil just days after a forest fire. The existence of these early behemoths presents a classic cosmic chicken and egg problem. How did the black hole come first? How did it gather so much mass, so astonishingly fast? One leading theory suggests they skipped the slow assembly line entirely. Instead of forming from the remnant of a single star, these black holes may have been born big, from the direct, catastrophic collapse of primordial gas clouds hundreds of thousands of times the mass of our Sun. It was a single, violent leap into existence. Another, even more intriguing possibility is that the early universe was seeded with a population of surprisingly heavy black hole precursors, jump-starting the growth process in a way we never anticipated. The location of these quasars adds another layer of mystery. They are often found in what we thought were pristine, relatively empty cosmic environments, regions that lack the rich fuel reserves needed for such rapid feasting and growth. Their presence there tells us that the conditions for creating the most extreme objects in existence were not rare or special. They were a fundamental part of the cosmic landscape from the very beginning. This forces a profound rewrite of the story of galaxy evolution. We can no longer think of galaxies forming first, and then slowly growing their central black holes over time. The evidence now suggests that the black holes and their galaxies grew up together, intertwined in a co-evolutionary dance from the dawn of time, each shaping the destiny of the other in ways we are only starting to understand. These galactic anomalies extend beyond their shape and size, reaching deep into their very chemistry. By carefully dissecting the faint light from these ancient star systems, astronomers can perform a kind of cosmic forensics, reading the elemental signatures imprinted within their spectra. The chemical composition of a galaxy is its life story, a permanent record of every star that lived, died, and scattered its enriched ashes back into the cosmos. Yet in these ultra-distant galaxies, that story contains baffling chapters we are struggling to read. The ratios of fundamental elements like nitrogen, carbon, and oxygen are completely unexpected, defying the established rules of chemical evolution. It is as if you followed a simple recipe for a cake, only to open the oven and find a dish with a completely different set of ingredients. One of the most puzzling signatures is a surprising overabundance of nitrogen. In our local universe, nitrogen is produced in significant quantities by specific, massive stars known as Wolf-Rayet stars. These are stellar powerhouses that burn ferociously and die young, expelling their outer layers in powerful winds. Finding so much nitrogen so early implies that entire generations of these particular stars had to form, evolve, and expel their material on an impossibly fast timeline. It suggests a stellar population that was skewed toward these massive, short-lived types, a demographic we did not think was possible in the universe's first communities. Another, even more profound possibility is that we are seeing the direct fingerprints of the very first stars to ever exist, the legendary population 3 stars. Theory suggests these primordial giants were behemoths, hundreds of times more massive than our Sun, composed only of hydrogen and helium. Their lives would have been brilliant and brief, ending in colossal explosions that for the first time seeded the cosmos with heavier elements. The unique nuclear fusion pathways inside these gargantuan stars could have produced a distinct chemical pattern, one that matches the strange abundances we are now observing. If confirmed, this would be one of the most significant discoveries in modern cosmology, our first direct glimpse at the stellar pioneers that lit up the cosmic dark ages. These anomalous chemical signatures are like cryptic messages from the dawn of time. Each unusual ratio is a clue pointing to a different type of stellar actor or a forgotten sequence of events in the universe's first dramatic acts. They force us to question not just the speed of galaxy evolution, but the fundamental nature of the first stars themselves. Were they different from the stars we see today? Did they follow a different set of physical laws in the pristine early cosmos? The answers are written in this ancient starlight, waiting for us to finally learn how to read them. This cosmic chemistry points to a deeper, underlying architecture, one that connects all galaxies into a single, vast system. We are beginning to see the universe's true skeleton, a structure cosmologists call the cosmic web. Picture the largest thing you can possibly imagine, and then think bigger. This web is a network of invisible filaments made of dark matter, stretching across the emptiness of space and connecting every galaxy cluster like cities linked by cosmic highways. For decades, this web was purely theoretical, a prediction of our best models. Now, for the first time, we are watching it light up. The brilliant glare from those early quasars and galaxies acts like a flashlight in a dark forest, illuminating the faint, wispy tendrils of gas that trace the web's hidden pathways. What we see is not the smooth, serene structure we expected. The primordial gas within these filaments is turbulent and clumpy, a frothing sea of matter. Even more telling, it is not uniformly neutral. We find vast, glowing bubbles where the gas has been ionized, its atoms stripped of their electrons. This patchwork of light and shadow reveals the complex, messy process of reionization, the moment when the first starlight burned through the cosmic fog that filled the young universe. It was not a single, swift dawn, but a staggered sunrise, with some regions clearing early while others remained shrouded in darkness. This turbulence has a direct consequence for the galaxies themselves. The smooth, steady flow of gas we predicted along these cosmic rivers does not exist. Instead, the fuel for star formation arrives in violent, clumpy waves, which could explain the explosive, stop-start bursts of creation we observe in the earliest galaxies. To see this web is to witness the fundamental blueprint of the cosmos, a dynamic and chaotic construction site where the very highways of matter are being forged. These chaotic pile-ups were not gentle encounters. The early cosmos was a cosmic demolition derby, a continuous and violent scramble where entire galaxies were torn apart and reassembled. In our local universe, a major merger is a headline event, a slow, billion-year dance that dramatically reshapes the galaxies involved. Back then, it was the norm. The James Webb Space Telescope reveals scenes of incredible complexity, with not just two, but often 3, 4, or even more galaxies caught in a simultaneous gravitational tug-of-war. Their shapes are stretched into long, luminous streams and tidal tails, beautiful and destructive evidence of their violent interactions. This constant state of collision solves several puzzles at once. It provides a direct mechanism for the rapid buildup of massive galaxies, as they cannibalize their smaller neighbors to grow large quickly. More importantly, it acts as the ultimate trigger for the intense starbursts we observe. When these giant clouds of gas collide, they do not simply bounce off each other. They compress, they shock, and they collapse inward under their own gravity, igniting firestorms of star birth on a scale we can barely comprehend. This hyper-social environment means that a young galaxy was rarely an island, quietly growing on its own. It was a participant in a relentless, high-stakes battle for material, its fate and its brilliance dictated by the company it kept. The very structure of the early universe, it seems, was built not in quiet isolation, but in a state of glorious, productive chaos. This deepening cosmic puzzle strikes at the very blueprint for building a universe. The models we use to simulate cosmic evolution are incredibly detailed, tracing the gravitational influence of dark matter from the first moments after the Big Bang. These simulations consistently produce a specific cosmic neighborhood. They show a large galaxy, similar to our Milky Way, living in a bustling community, its gravitational pull holding sway over hundreds of smaller, fainter dwarf galaxies. These tiny satellites are the predicted fossils of the earliest structures, the leftover building blocks from the universe's construction phase. Yet when we count the actual satellites around our own galaxy, the number falls drastically short. This is the classic missing satellite problem, a lingering mystery in our own backyard. But when we point our most powerful telescopes back to the era of the first galaxies, the problem does not just persist. It intensifies into a full-blown crisis. The early cosmos should be teeming with these nascent clumps of dark matter, each one a potential cradle for the universe's very first stars. Our observations, however, reveal a much quieter, emptier scene than anyone anticipated. Where are all the building blocks? One compelling explanation is that star formation simply failed to ignite in the vast majority of these small halos. Perhaps the intense ultraviolet light from the first massive stars blasted away the gas in these tiny structures, sterilizing them before stars could even form. This would leave behind a cosmos filled with dark, invisible halos of matter, full of potential but forever silent and unseen. Another, more radical idea is that the initial seeds of structure themselves were different. Maybe the dark matter particles interacted in ways that smoothed out the smallest clumps, leading to a universe that built fewer, but more massive, foundational pieces from the very start. This absence is not merely a missing detail. It is a fundamental challenge to our understanding of how gravity assembled the cosmos from the ground up, suggesting that the very first chapters of structure formation are a story we have not yet correctly read. Even the light we use to see the distant cosmos can be warped into a puzzle. The universe provides its own magnifying glass through a phenomenon known as gravitational lensing. When light from a faraway galaxy travels toward us, its path is bent by the immense gravity of a massive object in the foreground, like a giant galaxy cluster. This cosmic lens does more than just distort the image. It amplifies the light, allowing us to peer at galaxies that would otherwise be far too faint to detect. But this powerful tool is now revealing its own strange inconsistencies. In some cases, the lensing effect we observe around these ancient clusters is far stronger than it should be. The visible mass of the foreground galaxies is simply not enough to create such dramatic bending of space-time. The light is being twisted and magnified by something we cannot see. It is as if you were looking at a magnifying glass and realizing its power is far greater than the curvature of its glass should allow, hinting at an unseen hand pressing down. This missing mass could be the signature of countless small, dark clumps of matter, sub-halos that swarm around the main cluster like a cloud of unseen moons. Or perhaps it points to a more fundamental truth, that the dark matter in the early universe was not distributed in the smooth, predictable halos we see today, but was instead clumped into a more granular, lumpy architecture from the very beginning. These lensing anomalies give us a way to weigh the cosmos using gravity itself, a direct measurement of the invisible scaffolding that light can never show us. Every unexpected twist in a faraway galaxy's image is a clue, a faint signal from the dark foundation of reality, telling us that the blueprint we have been using is incomplete. The hidden architecture of the cosmos extends beyond dark matter to another invisible force. Magnetic fields weave through the spaces between stars, a cosmic framework that guides the flow of gas and the birth of new suns. We always thought these fields began as faint, disorganized whispers, slowly strengthening over billions of years as galaxies rotated and churned. This assumption has been shattered. We now have evidence of strong, well-ordered magnetic fields threading through galaxies when the universe was a mere fraction of its current age. It is like finding a sophisticated power grid already fully operational in the foundations of what should be a primitive, newly settled village. How could such coherence emerge from chaos almost instantly? The answer may lie in the violent dynamo of a young galaxy's birth. Imagine the incredible turbulence of those early gas clouds, swirling and colliding at fantastic speeds. This churning motion could have acted like a cosmic generator, rapidly amplifying a weak seed field into a powerful, organized force. But this just pushes the mystery back a step. Where did the original seed field come from? Some theories suggest it was imprinted on the fabric of the cosmos in its very first moments, a primordial fingerprint from a time before the first stars. The implications are profound. A strong magnetic field changes everything about how a galaxy behaves. It provides pressure that supports giant clouds of gas against collapse, potentially slowing star formation. At the same time, it can channel material along its lines of force, guiding flows that might later ignite stellar nurseries. This invisible hand was already at work, sculpting the earliest galaxies and adding a powerful, unexpected variable to the frantic equation of their evolution. The universe was not just building structure, it was wiring it with power from the very beginning. These ghostly islands of starlight represent a completely different kind of cosmic citizen. Among the brilliant, star-forming giants of the early universe, we are now finding the faintest, most ethereal objects ever detected, known as ultra-diffuse galaxies. Picture a galaxy the size of our own Milky Way, but containing only 1% of its stars. These are not dense, blazing cities of stars, but vast, dimly lit cosmic countrysides, where suns are spread so thinly that the darkness between them is almost absolute. In our modern, local universe, we find such ghosts, but they typically reside in the crowded environments of galaxy clusters, where gravitational forces can potentially puff them up or strip them down. The profound shock is that we are now spotting their faint signatures in the deep past, in the cosmic wilderness where no one expected such fragile things to survive. How does something so delicate and faint come into existence at the dawn of time? One possibility is that these are failed galaxies, cosmic underachievers that, for some reason, never mastered the art of star formation. Perhaps their dark matter halos had a unique structure that prevented gas from cooling and collapsing efficiently. Maybe they were born in a void, isolated from the cosmic flows of gas that fuel vigorous starbirth. Their immense, spread-out forms could be their original, pristine state, a road not taken by most galaxies. The other, more dramatic explanation is that they are the survivors of a cosmic wreck. These faint ghosts might be the remnants of once normal galaxies that were violently harassed and stripped of their gas and stars in a close encounter with a more massive neighbor. Their stars were not destroyed, but scattered into a vast, faint halo, a permanent record of a traumatic gravitational encounter. Finding them so early forces a difficult question. If they were stripped, the violence must have happened incredibly quickly, implying a level of galactic interaction we are only beginning to appreciate. If they were born this way, it means the universe was creating a stunning diversity of galactic structures right from the start, including these quiet, inefficient versions. Their very existence tells us that the cosmic dawn was not a monolithic era of frantic building alone. It was also a time that allowed for these strange, quiet outliers, these whispers from the past that challenge our very definition of what a galaxy can be. This final cosmic dawn was not a gentle sunrise. The epoch of reionization, when the first starlight burned through the universal fog, was far more chaotic than a simple, clean transition from dark to light. Our most distant observations reveal a universe lighting up in a scattered, uneven patchwork. Imagine a vast landscape shrouded in a deep, morning mist. Instead of the sun rising evenly to burn the fog away all at once, countless small campfires ignite at different times and in different clusters. Some clearings become bright and transparent quickly, while other valleys remain cloaked in shadow for eons longer. This is the patchy reality of reionization. The process was highly inhomogeneous, meaning the universe became transparent to ultraviolet light in a lopsided and gradual manner. This patchiness is a critical clue. It tells us that the first stars and galaxies were not sprinkled evenly across the cosmos like random seeds. They were born in specific, clustered neighborhoods, creating brilliant, isolated bubbles of clarity in the surrounding gloom. These bubbles then grew and merged over millions of years, eventually overlapping to clear the cosmic haze entirely. The timing of this grand finale is itself a source of surprise. Data suggests this universal transition did not end at a single, neat moment in time. Some regions completed their journey into transparency much earlier than others, stretching the process across a surprisingly long cosmic duration. This drawn-out conclusion forces us to rethink the power of the very first luminous objects. Perhaps the earliest galaxies were less efficient at producing the required ionizing radiation than we thought, needing more time to complete their cosmic task. Or maybe the fog of neutral hydrogen was denser and more stubborn in certain parts of space, resisting the initial waves of light. The story of the universe's first dawn is not one of a single brilliant flash, but of a slow, persistent struggle where light fought to carve out its dominion, one patch of sky at a time. These accumulating puzzles are now converging on a single, profound question. How solid is our fundamental blueprint for the entire cosmos? For decades, The Lambda cold dark matter model has stood as cosmology's foundational pillar, a grand narrative describing a universe dominated by dark energy and a slow-moving, invisible form of matter. Its success is undeniable, accurately predicting the large-scale tapestry of the cosmic web and the afterglow of the Big Bang itself. Yet when we point our telescopes to the universe's first chapters, to the small-scale behavior of infant galaxies, this elegant model begins to fray at the edges. The premature maturity of galaxies, the bizarrely lumpy dark matter halos, and the relentless, violent mergers we see are not just oddities. They are small-scale crises, each one a stubborn data point that the standard model struggles to accommodate without resorting to artificial fine-tuning. It is like having a master key that unlocks every door in a city, except for the very first rooms ever built. The architecture of those original structures is just different enough to defy our universal passkey. This does not mean the entire model is wrong. It is far too successful on larger scales to be simply discarded. Instead, these distant galactic anomalies are performing a vital function. They are conducting a brutal, real-world stress test on our core theories. The failure points they reveal are not in the dark cosmos itself, but in our understanding of the luminous one. The real shortcoming may lie in what physicists call baryonic physics, the complex dance of normal matter. Our simulations may not yet capture the full, turbulent story of how primordial gas cools, collapses, and ignites into stars, or how the fierce energy from those first stars and black holes subsequently pushed back against the dark matter scaffolding. Perhaps simple gravity was not the only force at play in those early times. Maybe dark matter particles interacted with each other or with normal matter in subtle ways that have since faded into insignificance, leaving a faint but detectable imprint only in the universe's oldest structures. These observations from the cosmic dawn are therefore more than just a collection of mysteries. They are a powerful guide, pushing us to develop more sophisticated simulations that better capture the feedback between light and dark. They are even encouraging a handful of physicists to cautiously explore modifications to the fundamental laws themselves. The ultimate value of these ultra-distant galaxies may not be the specific answers they provide, but the much deeper, more fundamental questions they are forcing us to ask. These first stars remain the ultimate ghost story of the cosmos. We call them Population 3 stars, the legendary pioneers of light. They were the universe's very first stellar generation, born from a pristine soup of only hydrogen and helium. Theory tells us they must have been colossal, hundreds of times more massive than our own sun, burning at ferocious temperatures and living lives that were brilliant and brief. Their deaths were not quiet affairs. They would have ended in cataclysmic explosions or direct collapses into black holes, and in doing so, they performed the universe's first act of alchemy. Forging the very first heavy elements in their cores, they seeded the empty cosmos with the raw ingredients for everything to come: the carbon, oxygen, and iron that would later form planets and life itself. Yet for all their profound importance, we have never directly seen one. They are cosmic phantoms, vanishing before our most powerful telescopes can peer back far enough to witness their blaze. The hunt for them is the pinnacle of cosmic archaeology, a search for the foundational ancestors of all subsequent structure. So how do you find a ghost? You look for its shadow. Astronomers are now searching for the unique chemical fingerprints these behemoths would have left behind in the light of the earliest galaxies. The signature would be unmistakable, a complete absence of any metals, which is the term astronomers use for any element heavier than helium. Paired with that pristine purity, we would expect to see unusually strong spectral lines from helium itself, a testament to the unique nuclear fusion that occurred in those gargantuan furnaces. We are now seeing tantalizing hints of this very pattern in the spectra of some ultra-distant galaxies. The chemical abundances are weird, They do not match what later generations of stars produce. It is like finding an ancient artifact made from an unknown alloy, a material that could only have been crafted by a lost civilization. If confirmed, this would be one of the most significant discoveries in modern science, finally providing direct evidence for the stellar engines that ended the cosmic dark ages. It would confirm the initial conditions for everything we see today, revealing the ultimate origin of the elements that make up our very world and ourselves. The pursuit of these first lights is more than a technical challenge. It is a journey to our own cosmic origin, a quest to witness the moment the universe first learned how to shine. The very engines of creation also possess the power to erase. At the heart of many young, brilliant galaxies, a monster was stirring, one that could dictate the future of its entire cosmic home. We call this phenomenon active galactic nuclei feedback, and finding it in full force during the universe's first chapters is a breathtaking discovery. An active galactic nucleus is the furious core of a galaxy, where a supermassive black hole is actively feeding. As vast quantities of gas spiral into its gravitational grip, the material compresses and heats to unimaginable temperatures, releasing a storm of energy that can outshine every star in the galaxy combined. But this is more than just a brilliant beacon. That incredible power does not just radiate out peacefully. It can drive colossal winds, hurricane-force outflows that blast through the galaxy and blow the raw fuel for star formation. The cold, dense gas clear out into intergalactic space. This is the essence of feedback, a self-regulating mechanism where the black hole effectively shuts down its own food supply and the galaxy's ability to make new stars. We have seen this process in the modern, local universe, a kind of cosmic middle age. But to witness it in a galaxy only a billion years old is like finding a toddler who not only runs a company, but has already instituted a corporate hiring freeze. The evidence comes in the form of twisted spectral lines. Astronomers see the light from hot gas in these primordial galaxies, but its signature is stretched and skewed, indicating it is rushing away from the galaxy's core at velocities of thousands of kilometers per second. These are not gentle breezes. They are tsunamis of energy capable of stripping a galaxy of its future. This changes the entire narrative of co-evolution. We knew black holes and their galaxies grew up together, but we thought the black hole was mostly along for the ride, growing passively as the galaxy evolved. These outflows tell a different story, one of active, dominant regulation. The black hole was not a passive passenger. From a remarkably young age, it was a commanding force, its violent outbursts seeding the surrounding space with enriched material while simultaneously placing a hard limit on how many stars its galaxy could ever create. This early, intimate tango between star formation and black hole activity suggests a relationship far more influential and tightly wound than we ever dreamed. A fundamental partnership that was set in stone, or rather in gravity, from the very beginning. This cosmic ghost hunt leads us to one of the most elusive concepts in all of astronomy, the dark galaxy. Picture a vast, swirling cloud of primordial gas, possessing all the mass and structure of a true galaxy, yet shrouded in an almost perfect darkness. It is a ship with a full hull, built and ready to sail, but with no lanterns lit. These hypothetical objects are the silent, unseen pioneers predicted by our models, the building blocks that never quite caught the spark of creation. For decades, they existed only in theory, but now we are finding tantalizing candidates in the deep field observations from our most powerful telescopes. We do not see them directly. Instead, we detect their faint, ghostly presence through two primary methods. Sometimes we catch a whisper of specific emission lines, a faint glow from hydrogen gas that is not being lit up by any visible stellar population. Other times, we infer their mass through the subtle warping of space-time, a gravitational lensing effect that reveals an invisible clump of matter with the heft of a galaxy. yet with no light to account for it. The confirmed discovery of a true dark galaxy would be a monumental paradigm shift. It would prove that a significant portion of the universe's foundational structures failed to ignite, remaining as cosmic stillbirths. Why would a galaxy full of fuel never form stars? The reasons could be as profound as they are varied. Perhaps the gas within these dark halos was never able to cool and fragment into the dense, cold clumps necessary for stellar birth. Maybe they were born in cosmic voids, isolated from the triggering shockwaves of galactic collisions that sparked their brighter cousins. Or their fate could have been sealed by external forces, their gas sterilized by the intense, blistering radiation from a nearby quasar or a bustling cluster of early galaxies, a process known as photoevaporation that stripped away their star-forming potential before it could even begin. Finding a population of these objects would complete our cosmic census, revealing a hidden channel of galaxy formation that has so far eluded our direct observation. It would show us that the path to a luminous galaxy was not the only road available. Some structures took a different, quieter path, choosing to remain as dark, gas-rich monuments to potential, forever holding the secrets of the universe's first, unlit dawn. This introduces a profound, almost philosophical challenge to our entire quest. Our entire view of the early universe is filtered through a keyhole. We call this limitation cosmic variance. Think of it like trying to understand the entire planet Earth by studying a single city. If your only view was of New York City, you would naturally conclude that human civilization is a dense, vertical, and ceaselessly active phenomenon. You would have no concept of the vast, quiet deserts, the sprawling farmlands, or the sleepy coastal villages that make up the rest of the world. Our most powerful telescopes, for all their might, operate under the same constraint. They peer into incredibly deep but remarkably narrow fields, tiny postage stamps on the vast envelope of the sky. The stunning anomalies we have been discussing, the overabundance of massive galaxies, the frantic rates of star formation, the unexpected mergers, all of these could be amplified because we are looking at a cosmic metropolis. We might be studying the universe's equivalent of a downtown financial district during rush hour. A different patch of sky, a quieter cosmic neighborhood, could reveal a much calmer, more sparsely populated universe, one that aligns far better with our traditional models. This sampling error is not a flaw in our instruments, but a fundamental limitation of our position in space and time. It means that every breathtaking discovery from the edge of time comes with an invisible question mark. Is this a universal rule or just local zoning? The only way to know for sure is to broaden our survey, to map vast swaths of the sky with the same incredible depth. As we do, the features we think are absolute truths today might soften, or they might intensify, revealing a cosmos far more varied and complex than we ever anticipated. Our understanding of the beginning of everything is, and may always be, a work in progress, a picture we are patiently assembling one tiny, brilliant piece at a time. This constant tension between prediction and reality is the engine of science itself. For decades, cosmologists had a powerful tool, the Lambda cold dark matter model, which they used to run immense cosmic simulations. These digital universes, born from equations and computing power, painted a specific picture of what our telescopes should see when looking back to the beginning. The reality delivered by the James Webb Space Telescope and its predecessors has been far richer, far stranger, and far more puzzling than any simulation ever produced. This is not a failure of science. It is its greatest success. The startling discoveries of impossibly mature galaxies and bizarre dark matter behavior are not roadblocks. They are guideposts, forcing theorists to return to their drawing boards with a wealth of new clues. The response has been a creative explosion in model building. Scientists are now tweaking the virtual laws of physics within their simulations to see what could possibly create the cosmos we observe. They are testing scenarios where the very first stars formed with unimaginable efficiency, converting gas into suns at a rate that defies our old assumptions. They are exploring the idea that dark matter is not completely cold and non-interacting, but might have been able to bump and jostle in the early universe, smoothing out its distribution into the lumpy halos we detect. The role of feedback, the powerful winds from stars and black holes that can shut down star formation, is being amplified in these new models, as is the potential influence of magnetic fields from the very dawn of time. Some are even taking a more radical step, cautiously exploring whether the laws of gravity themselves might need a slight adjustment on the largest cosmic scales. This entire, vibrant process is a beautiful, iterative dance. Observation delivers a surprise. Theory scrambles to explain it, proposing new mechanisms and making fresh predictions. Those predictions then guide the next round of observations, which either confirm the new ideas or present yet another, deeper mystery. We are living in a golden age of this dialogue, a time when each new data release from a space observatory is not just an answer, but a new set of questions, challenging our oldest assumptions and pushing our understanding of the cosmos into uncharted territory. Every discovery from the cosmic dawn is a triumph snatched from the edge of invisibility. The signals we chase are among the faintest ever measured, whispers of light that have traveled for over 13 billion years, only to dwindle into a handful of photons by the time they reach our instruments. Capturing this ancient glow pushes our technology to its absolute breaking point. The James Webb Space Telescope, our most powerful window into the past, represents a monumental leap in sensitivity. Yet even this engineering marvel strains against the fundamental limits of detection. To gather enough light from the most distant galaxies, it must stare at a single patch of sky for dozens, sometimes hundreds of hours, a painstaking process akin to holding a cosmic exposure. Each pixel in the resulting image is precious, a tiny data point wrestled from the relentless noise of the universe itself. This is not a failure of our tools, but a testament to the incredible challenge of witnessing the birth of the first cosmic structures. The very fact that we are bumping against these boundaries is a thrilling signpost, pointing toward a future ripe with revelation. The next generation of observatories is already on the horizon, designed to shatter these current limits. The Nancy Grace Roman Space Telescope will open a panoramic window to the cosmos, with a field of view over 100 times larger than Hubble's infrared instrument. This vast perspective will allow us to move from studying a few brilliant, anomalous galaxies to conducting a true statistical census of the early universe. We will see not just the spectacular outliers, but the quiet, average citizens of the cosmic dawn, finally understanding the full population of infant galaxies. On the ground, the extremely large telescopes, with their colossal mirrors spanning nearly 40 meters, will provide razor-sharp resolution, allowing us to dissect the internal structure of these faraway systems in unprecedented detail. We will watch gas flowing into them and powerful winds blowing out, witnessing the dynamic processes of their growth and self-regulation in real time. The greatest discoveries about the ultra-distant universe are not behind us. They are waiting, just beyond our current grasp, for the next generation of eyes that will look back and finally see the dawn in all its intricate, chaotic, and magnificent glory. These galactic anomalies reach far beyond the telescopes and the data. They strike at the very core of our philosophical understanding of the cosmos, forcing us to re-examine a principle that has guided science for centuries. This is the Copernican principle, the profound idea that we do not occupy a privileged or special place in the universe. We have always assumed that the physical laws we measure here and now are the same everywhere and for all time, a universal constant. Yet the infant universe presents us with a scene of such bizarre and rapid construction that it quietly challenges this foundational belief. If the rules are truly identical, Why did the early cosmos build galaxies with such frantic, almost frantic efficiency, a pace that seems to have slowed dramatically in our own cosmic era? This is not merely a question of speed. It is a question of fundamental behavior. Are we certain that the constants of nature, the strength of gravity or the force binding atoms, have remained perfectly fixed since the dawn of time? Or could there have been subtle, undetected variations in those first moments, creating a realm with a slightly different set of physical rules? The sheer strangeness we observe humbles our deepest intuitions. We are creatures of a mature, orderly cosmos, and we naturally expect that complexity develops slowly and gradually from simple beginnings. The universe, it seems, had a different idea. It produced intricate, mature structures almost immediately, operating by a logic that feels profoundly alien to our own anthropocentric expectations. This journey to the cosmic dawn is therefore more than an astronomical survey. It is a voyage into the nature of reality itself, forcing us to consider that the universe is not only vaster than we suppose, but stranger in its history and its foundational principles than we ever dared to imagine. This immense flood of cosmic data has sparked a quiet revolution in who gets to make a discovery. The images from our great telescopes contain millions of galaxies, a deluge of information so vast that the global community of professional astronomers could never hope to sift through it all alone. The solution has been to open the doors of the cosmos to everyone through the power of citizen science. Online platforms now allow volunteers from all walks of life to look at the same deep-field images that baffle experts, classifying galaxy shapes, noting strange features, and searching for the subtle clues that might lead to the next breakthrough. There is a unique magic in the human brain's ability to recognize patterns and spot outliers, an intuitive skill that even the most sophisticated algorithms can struggle to replicate. It is a deeply collaborative effort, a global project where a teacher in Buenos Aires or a retiree in Tokyo can be the first human eyes to notice a peculiar smudge of light that turns out to be a never-before-seen type of galaxy. Several of the most curious objects in the deep fields, the ones that defy easy categorization, were first flagged by these dedicated amateur scientists. This process does more than just accelerate research. It fundamentally democratizes the act of discovery itself. It transforms the search for truth at the edge of the observable universe from an exclusive academic pursuit into a collective human endeavor. A shared journey of curiosity that reminds us that the desire to understand the cosmos is a universal part of our nature. The chemistry of life itself is written in the light of these ancient galaxies. Every atom of carbon in our bodies, every breath of oxygen we take, was once forged in the heart of a star that lived and died long before our sun was even a glimmer in the cosmos. The profound revelation from the early universe is that this stellar alchemy was not a slow, gradual process. The essential ingredients for planets and for biology were being manufactured and scattered across the cosmos with breathtaking speed. In the hearts of those first, frantic galaxies, generations of stars were completing their entire life cycles, from birth to explosive death, seeding their surroundings with enriched material. This means that the universe became chemically mature far earlier than anyone had predicted. The cosmic kitchen was open for business, and it was serving up the elements for potential life almost immediately. If a planet could coalesce from the dust around a star in one of those early galaxies, the fundamental building blocks for life would have been right there, mixed into the planetary batter from the very beginning. This does not mean we have evidence that forests grew under alien suns 13 billion years ago. It means the universe achieved a state of chemical readiness for life astonishingly quickly. The possibility for biology, however remote, was pushed billions of years further back into cosmic history. The frantic, mature, and unexpectedly efficient galaxies we are discovering are not just cosmic curiosities. They are the very foundries that may have set the stage for life's eventual emergence, turning the raw simplicity of the Big Bang into a complex, chemistry-rich universe capable of one day asking questions about its own origin. Our cosmic yardsticks may be bending under the weight of time. To map the immense void between galaxies, astronomers depend on a class of celestial objects known as standard candles. Think of these as cosmic lighthouses, beacons whose true, intrinsic brightness we believe we understand. By measuring how dim they appear from our vantage point, we can calculate their distance with remarkable precision. This method relies on a profound assumption that a supernova exploding in a distant galaxy 13 billion years ago behaves identically to one we observe in our modern cosmic neighborhood. But what if that fundamental assumption is flawed? The earliest stars were forged from a different recipe, a pristine blend of hydrogen and helium almost entirely free of the heavier elements that fill our sun. This pure composition could have radically altered how these pioneer stars lived, burned their fuel, and ultimately died. A star with less metal, as astronomers call these elements, might evolve faster, burn hotter, and explode with a different kind of fury. If the supernova in the infant universe were systematically brighter or fainter than their modern counterparts, then our entire distance ladder becomes unstable. A galaxy we thought was exceptionally bright and massive might, in reality, be much closer and more ordinary. Conversely, a truly bizarre object could be hiding in plain sight, its strangeness masked by a miscalibrated measurement. This is the subtle, haunting uncertainty that underlies every claim about the early cosmos. The very tools we use to measure reality might be changing over time, forcing us to question not just what we see, but the reliability of our own vision. How can we be sure of any anomaly when the ruler itself might be stretching? The signals we have gathered so far are only one part of the conversation. For all of human history, our entire understanding of the cosmos has been built upon a single messenger, light. We have become masters of decoding its wavelengths, from the gentle heat of infrared to the furious blast of gamma rays. Yet light can be blocked, scattered, and absorbed. It gives us a brilliant but ultimately filtered view of reality. We are now on the cusp of a revolution that will shatter this single-sense limitation, an era known as multi-messenger astronomy. This new frontier invites us to listen to the universe as well as look at it, to feel the very fabric of space-time ripple with cosmic events. Imagine trying to understand a thunderstorm by only seeing the lightning. You would miss the deep, rumbling thunder that carries its own unique information about the storm's power and distance. In the same way, the most violent events in the early universe, like the mergers of the first supermassive black holes, would have sent out not just brilliant flashes of light, but titanic ripples in spacetime itself, gravitational waves that have been traveling across the cosmos for over 13 billion years. We cannot yet detect these particular ancient ripples. They require a new kind of observatory, one that operates not on a mountaintop, but in the pristine quiet of space. Projects like the Laser Interferometer Space Antenna, or LISA, are designed to be our ears for this primordial thunder. By placing 3 spacecraft in a perfect triangular formation, millions of kilometers apart, they will sense the infinitesimal stretching and squeezing of space as a gravitational wave passes by. A detection from the cosmic dawn would be a direct, unmediated signal from the event itself, completely independent of the light it may or may have not produced. This synergy is the true power of the multi-messenger approach. Light tells us what an event looked like and what elements were forged. Gravitational waves would tell us the precise masses of the objects involved and the brutal dynamics of their final dance. Add to this the ghostly particles called neutrinos, which can escape from the hearts of collapsing stars without being deflected, and you have a complete sensory picture of a cataclysm. This triangulation of truth could resolve our deepest mysteries in an instant. Is the dark matter distribution in an early galaxy truly lumpy? A gravitational wave signal from a merger within it would precisely measure the total mass involved, dark and light combined, giving us a direct way in. Are the chemical anomalies we see from the first stars correct? A neutrino burst from one of their deaths would confirm the unique nuclear furnaces at work. We are moving from watching a silent movie of the universe's birth to experiencing it in full, immersive detail, with sight, sound, and touch. This is not merely a new telescope, it is a new sense, and it promises to reveal a cosmos far more vivid and dynamic than we have ever dared to imagine. Our journey to the edge of sight has revealed a cosmos of beautiful chaos, a realm where infant galaxies behaved like seasoned adults and dark matter clumped into unexpected shapes. Each of these distant anomalies is more than a simple puzzle for astronomers to solve. Together, they form a chorus of cosmic descent, challenging the foundational theories we have trusted for generations. The early universe refuses to be a quiet, primitive backdrop. It was a frenetic and profoundly innovative laboratory, operating on a timescale and with a set of rules we are only just beginning to translate. These are not failures of our models but glorious signposts, pointing unequivocally toward new physics and a grander narrative of cosmic evolution. As our telescopes peer ever deeper into the past, let these profound mysteries ignite not frustration, but a deep and humbling wonder. The universe has proven itself to be infinitely more ingenious than our boldest imaginations. The greatest revelations are still waiting, hidden in the faintest whispers of ancient light, for the next generation of curious minds to finally bring them into view.